You've seen a dam on TV or in a photo. Massive concrete wall, water pressing against it, and somewhere near the top, a row of heavy steel gates holding everything back. Those gates sit in rushing water for decades, 50 years, sometimes longer, and somehow they don't rust apart. You'd think it's special steel, maybe some kind of heavy-duty paint. But the real answer is something most people have never heard of, an invisible system that tricks corrosion into attacking the wrong target. And that same system is protecting the bridges you drive over and the pipes underneath your street. Here's the thing most people get wrong about infrastructure. They think rust is a surface problem, a cosmetic issue, something you sand off and repaint. But corrosion is the single most expensive material failure in the modern world. In the United States alone, the cost of corrosion adds up to roughly $1,400 per person per year. That's not a rounding error. That's a national-scale economic drain happening quietly across every bridge, every pipeline, every water tank, and every spillway gate touching moisture right now. And nearly all of that steel is the same basic stuff, mild steel. Just iron and carbon, not exotic alloys, not space-age composites. Plain, simple, affordable metal that happens to be excellent at holding up structures and terrible at resisting water. So why not just use stainless steel and solve the problem? Because stainless costs roughly 5 times more than mild steel for the raw material alone, and it's significantly harder to weld and fabricate in the field. Building an entire dam spillway system out of stainless steel would be like paving your driveway with marble. Technically possible, financially insane. So engineers are stuck with a fundamental trade-off. The metal they can afford to build with is the metal that wants to fall apart the moment it gets wet. That means the entire game becomes protection. Keep the water away from the steel, and the steel survives. The most obvious answer is paint. A physical barrier between moisture and metal. And paint works genuinely well for a lot of applications. But it has hard limits. It chips. It cracks. It wears down under UV and weather and constant water flow. And here's the big one. You cannot paint rebar that's already buried inside concrete. Once that steel is encased, no brush is reaching it. So if paint can't do the job alone, what actually protects the metal nobody can see? That's where the real engineering begins. Most people picture rust as a simple process. Water touches metal, metal turns orange, metal gets weaker. That's the version you learned in school, and it's not wrong, but it's missing the entire mechanism underneath. Corrosion isn't just a chemical reaction. It's an electrochemical process, which means it behaves like an electrical circuit. And once you understand that, the whole picture changes. Here's how it actually works. 2 separate steps have to happen for steel to corrode. The first is called oxidation, where the metal loses electrons. The second is called reduction, where those electrons get picked up somewhere else. These 2 steps don't happen in the same spot. They happen at different locations on the surface of the metal, connected by the flow of electrons through the steel itself. The areas that lose electrons are called anodes. The areas that receive them are called cathodes. The anode corrodes. The cathode doesn't. It's that simple and that specific. But here's the part that surprises people. This entire circuit can happen on a single piece of steel. You don't need 2 different metals. Different spots on the same piece of metal can carry slightly different electrical charges, and that tiny difference is enough to set up the whole corrosion process. One patch becomes the anode, another becomes the cathode, and electrons start flowing between them. Rust doesn't appear randomly. It follows an invisible electrical map across the surface of the metal, attacking some areas while leaving others untouched. This is why rust shows up in clusters and pits instead of spreading perfectly evenly across a surface. The corrosion is chasing voltage differences you can't see with your eyes. And that's actually the key to everything that comes next. Because if corrosion works like an electrical circuit, then engineers can manipulate that circuit, They can redirect it, control it, and force it to attack something else entirely. So if corrosion is an electrical circuit, the question becomes, how do you reg the game? The answer starts with something called the galvanic series. It's essentially a ranking of metals based on how resistant they are to corrosion, a nobility chart. The more noble a metal is, the less it wants to corrode. Gold sits near the top, titanium is up there, steel is not. Steel sits near the bottom of the list, meaning it corrodes easily in most environments. But here's where it gets clever. When you join two different metals together and expose them to moisture, the less noble one becomes the anode and starts corroding. The more noble one becomes the cathode and gets protected. The corrosion circuit still runs, but now it has a preferred target. And a few common metals sit even lower than steel on the galvanic series. Zinc, aluminum, and magnesium are all less noble. Attach any of them to steel, and they sacrifice themselves so the steel doesn't have to. That's the entire principle of cathodic protection. Give corrosion a victim it prefers, and the structure you care about stays intact. The most familiar version of this is galvanizing, which means coating steel in a thin layer of zinc. The zinc works as both a physical barrier and a sacrificial anode at the same time. It's cheap, it's effective, and it's everywhere. Nearly every piece of exposed steel infrastructure uses some form of zinc coating. Building framing, handrails, stairs, cables, sign structures, outdoor nails, screws, even rebar in certain high-value concrete projects. But galvanizing has hard limits. It's a factory process that requires dipping entire assemblies into giant baths of molten zinc. You can't re-galvanize a structure in the field once the coating wears through. And in aggressive environments like coastal areas or regions that dump de-icing salt on roads, a thin zinc layer doesn't survive long. So if galvanizing wears off and you can't reapply it in the field, what do? You bolt the anode directly onto the structure and replace it when it's used up. That's exactly what engineers do on underwater and underground infrastructure. Chunks of zinc, aluminum, or magnesium get attached to steel structures and left to corrode on purpose. When they're eaten through, you unbolt them and attach fresh ones. It's the same galvanic principle, just made replaceable. But not all sacrificial metals perform the same way. Testing shows that each one involves a clear trade-off. Unprotected steel corrodes deep and fast, with thick pockets of rust eating into the surface aggressively. Magnesium offers the strongest protection, pulling almost all the corrosion away from the steel, but it burns through incredibly quickly. In controlled testing, a magnesium anode can be nearly gone in just 3 weeks. Zinc protects well and stays mostly intact over the same period. Aluminum sits somewhere in between. Stronger protection means faster anode consumption. That's the math engineers have to balance depending on the environment, the budget, and how often someone can physically get to the structure to swap parts. And here's where it matters in the real world. The Howard Franklin Bridge in Tampa carried roughly 180,000 vehicles a day across Old Tampa Bay. By the mid-1980s, after less than 30 years in a harsh coastal environment, the steel reinforcement inside its concrete was corroding so badly that the Florida Department of Transportation was preparing to replace the entire bridge. That would have been enormously expensive and disruptive. Instead, they tried something cheaper first. Zinc was applied around the outside of concrete girders and wrapped around foundation piles, then electrically coupled to the rebar inside. The zinc became a sacrificial anode, pulling corrosion away from the structural steel. That provisional fix extended the bridge's working life to over 60 years. Sacrificial anodes work, but they have a ceiling. They rely entirely on the natural voltage difference between two metals. And in some environments, that difference isn't strong enough to protect the structure fully. So engineers built a way to force the issue. It's called impressed current cathodic protection, and it takes the same basic principle and adds an external power source to guarantee the electrons flow in the right direction. Instead of bolting on a chunk of zinc and hoping the galvanic series does enough work, an impressed current system uses a rectifier to push electrical current through the circuit deliberately. The steel is forced to act as the cathode no matter what. The voltage involved is surprisingly small, just a few volts, roughly the same as a typical AA battery. But the current flowing through the system can reach tens or even hundreds of amps. That's a tiny push, creating a massive protective effect across enormous structures. This isn't optional in a lot of cases. In many jurisdictions, buried pipelines are legally required to have impressed current cathodic protection systems installed. A corroded pipeline doesn't just fail mechanically. It leaks, and a leaking pipeline can cause enormous environmental damage, contaminating soil and groundwater for years. The legal mandate exists because the consequences of skipping protection are that severe. If you've ever noticed small equipment panels or metal test stations sitting along a pipeline right-of-way, especially near road crossings, that's the visible surface of an underground cathodic protection system doing its job quietly. The Howard Franklin Bridge used both approaches together. Sacrificial zinc anodes handled the baseline protection, while impressed current systems reinforced the most vulnerable areas. Layered defense. And that's common practice on critical infrastructure where failure carries massive consequences. The spillway gate from the opening of this script isn't relying on one trick either. It's wrapped in a protection system designed with redundancy because when the structure matters, one layer is never enough. Here's the part that sharpens the whole picture. The Howard Franklin Bridge wasn't saved by some breakthrough technology or a massive construction project. It was saved by spending a little money early instead of a lot of money later. Decades of cathodic protection cost a tiny fraction of what tearing down and rebuilding the bridge in the 1980s would have. And that math repeats everywhere in infrastructure. Maintaining and rehabilitating what already exists is almost always cheaper, uses fewer resources, and causes less environmental disruption than ripping it out and starting over. An ounce of prevention, applied correctly, can buy decades of service life that no one expected to get. But here's the surprise. You've been living inside this system your entire life without noticing it. The water main running under your street right now has sacrificial anodes corroding quietly, so the pipe doesn't. The bridge you drove over this morning has zinc buried inside its concrete, pulling corrosion away from the rebar holding the whole thing together. The gas line feeding your neighborhood has an impressed current system humming along with a small rectifier box sitting on the surface, and you've probably walked past it 100 times without a second glance. Every spillway gate sitting in water, every offshore platform standing in salt water, every underground storage tank at a gas station, they all depend on metal that was installed specifically to be destroyed. Corrosion is one of the primary ways infrastructure deteriorates, and cathodic protection is the frontline defense against it. Without these systems, bridges would need replacement twice as often, pipelines would leak constantly, and the cost of keeping the built world standing would be staggering. The system nobody sees is the system holding everything together. It runs silently, corrodes on schedule, and gets replaced before the structure it's protecting ever knows the difference. So that spillway gate sitting in rushing water for 50 years isn't surviving by luck. It's not special steel. It's not thicker paint. There's an invisible electrical system running through it right now. Sacrificial metal corroding on purpose, so the gate doesn't have to. Engineers designed it to lose a small battle so the structure wins the war. Every bridge, every pipeline, every gate submerged right now is protected by metal that was installed specifically to be destroyed. That's not a flaw. That's the design. And if you enjoyed this video, make sure to subscribe for more content just like it.